Hi there, Rachel Chase here, and in this video we will continue to explore the measures of variation used in statistics. So let's start with one that we've probably heard about before, and that is the range. To calculate the range of your data set, we take the max of our values minus the minimum value. Now, you might wonder, well, how is this considered measure of variation? Measures of variation are also known as dispersion. So we're curious how much variety, if you will, or how much dispersion does our data set have? So what the range does is tell us how wide of a gap is there between the biggest value and the smallest value. Now, it's not as heavily used as some other things, such as standard deviation and variance. So a few formulas that we'll need throughout this unit, and I'm going to show you both sets here. You'll notice that our standard deviation calculations are exactly the same as the variance with the addition of the square root. And that is because no matter what type of data you have, the standard deviation is always equal to the square root of the variance. So if you can't remember how to go between each, go to get the standard deviation, you take your square root of the variance. So essentially when you're doing these by hand, in another video, we'll explore how to calculate these using a graphing calculator. Once you find your variance, it's one last step. So let's go ahead and play around with a few questions, and then in a follow-up video, you'll see how we can use technology to alleviate some of this for us. So how do we calculate the standard deviation and also the variance in this case? First things first is we have to identify what is the data like. So is it a population set of data? Is it a sample set of data? So here they tell us the first exam scores for an entire section of Math 181 are given below. Notice how they've specified here. It's the entire section. If you have an entire set of data, we have to assume that that's population data. So if this is population data, let's reference back to our formulas here. Now, bear in mind you will be provided these formulas on an exam. However, you won't necessarily have to, use them if you're using technology, etc. But for now, we're going to practice so we can see how these formulas work together. Now, because we've identified that this is a population set of data, we're going to use our population standard deviation and variance formulas. You'll notice that this symbol, much like mu, is used to denote the population standard deviation always. And if you're wondering how do I say that, that is a lowercase sigma. So earlier we saw uppercase sigma was to take the sum, just as we see here. Lowercase sigma represents the population standard deviation. So I'm going to use this formula since we've decided on population data. I'm just going to copy it over here to remind us. That's one thing that's a good habit to get into, is to write the formula at the top of the question that you're working with, just to remind you what it is that you need to practice. So you'll notice, similar to what we learned earlier with group data, is we have to use an order of operations here. So this tells us to take the sum of x minus mu squared and divide all of that by n. Well, what is x? Earlier we said x is every single data value, so each one of these test scores represents an x. So the first thing I need to do here is make myself a list. So I'm going to make a list of my x values and just copy them over. It's nice if you set them up vertically because it does let you use this chart method pretty easily, which a lot of people like that type of organization. Now that we have all of our data listed, we need to first, according to this formula, use order of operations. Numerator, parentheses first, x minus mu. If I haven't yet calculated that, and you'll notice it's not given here, we first need to find out what mu is equal to. So mu equals, add all of our numbers up, and divide by the total. So we have here a mean of 87.2 and a sample size, or I'm sorry, a population size of 6 test scores, so it was a very small class. Now that we have our mean, I'm going to take each one of these values and subtract that mean from it. So take a moment. We have 81 minus 87.2 is negative 6.2. 95 minus that is 7.8. Then we have negative 13.2, 10.8, negative 0.2, and last but not least 0.8. So this right here takes care of inside the parentheses. After parentheses, we do our exponents next. So what that tells us for this problem is I'm going to go ahead and create another column and call that x minus mu squared. So I'm taking each one of these values and raising them to the second power. Don't forget, when you square a negative number, it becomes positive. So if you're using your calculator for this, be careful because you have to make sure that the negative is inside the parentheses. I'm going to go down the list here and just write out what these are. Now that we have all of our squared values listed out, the formula tells us to take the sum of all of those numbers. So just as we did earlier, I'm going to include a total here. So I'm going to take my sum, and that sum is equal to 390.84. Now, if my standard deviation is the square root of all of this, the first thing I'm actually going to find is my variance. So my variance is equal to this number here, 390.84, divided by n is equal to 6. Now, before I do anything in terms of whether I have to round or not, I'm also going to list out what that would be for my standard deviation, and that is the square root of this number up here. One thing you have to be careful with is if you rounded your answer for variance, you cannot use the rounded answer when you take the square root. So let's take our calculator and take a look at what these would be. So our variance is 65.1 or 65.14. So one rounding habit that we often get into, and you'll see this when you're working through your MyLabs Plus homework, is that you go one decimal place at least beyond what your data set has. So you'll notice all of our values were whole numbers, so our mean we rounded to one place. So if you wanted to, you don't have to, but if you wanted to, you could round this to 65.1. Now, what I was saying before was for the sake of accuracy, you cannot use this rounded number in this problem. However, since it's exactly 65.14, if I go back to my calculator here, I'm going to go ahead and take the square root of that number, which gives me 8.0709. So this is approximately 8.0709. At this point, if you want to round, that would be 8.1. So while it's great that we have this standard deviation and variance, the goal is to interpret. So here's a good point for us to say, the higher the standard deviation, the higher the variety within your data set. So the one thing, as simple as that might sound, high standard deviation, high variance, you have to consider what your mean actually is. After we finish up calculating standard deviation and such, we're going to look at something called the coefficient of variation, which will give you the kind of hard answer of, is there a lot of variety, yes or no? So stay tuned for that. Just like we did earlier when calculating means, we're next going to take a look at dealing with group standard deviation. Group standard deviation is roughly the same process, but it does have a little bit of an added step. Now, if you recall from dealing with our measures of center, grouped means we first had to find and fill out what our midpoints were. So take a moment and fill in the midpoint for each interval that you have, and then we can progress forward. So with our midpoints, you'll see if we go back to our formula page that dealing with group data is roughly the same concept as dealing with it for means. You'll notice that the formula is very similar, only now we have the add-in of dealing with the frequency. So in other words, how often each of those occurs. Furthermore, you'll see also with sample standard deviation, we divide by n minus 1 instead of n. So let's go through and work out this problem. After I find my midpoints, I'm going to first create a column for each midpoint minus the sample mean. Up here, they've already told us that our sample mean is equal to 103.5. So first things first, take each midpoint and subtract 103.5. That gives us negative 24, negative 4, and positive 16. Next, we're going to square each of those values, just like we did earlier. So negative 24 squared, we have 576, negative 4 squared, positive 16, and 16 squared, we have 256. Now this is where things derail a little bit. Because we have this as a frequency distribution, each of these squared values must first be multiplied by the respective frequencies to weight them according to how often they occur. So I'm going to have one final column for my frequency times each of those, which gives me 1 times 556 is 576, sorry. We have 10 times 16, 160, and 4 times 256, 1024. At this point, we can go ahead and take the sum of that column to get the numerator of what goes under the square root there. So this adds up to 1,760. I know this seems very time-consuming, but we're in the home stretch. Our sample variance, let's start with that, is equal to 1,760 divided by n is the sum of our frequency we find is 15. So we have to do 15 minus 1. So that is 1760 divided by 14. So that gives us, as you can see, a whole long decimal here. So that's approximately 125.7. Now our standard deviation is equal to the square root of this 1760 divided by 14. So again, as we talked about earlier, you have to be very careful. You cannot use this rounded number. Instead, take the square root of the entire thing. So that gives us 11.212, so just about 11.2. So what does that mean? With this set of sample data, we have a mean of 103.5 and a standard deviation of 11.2 points in terms of IQ. So the question is, what does this tell us? What can we learn from this? So to do that, we first have to talk a little bit about position in terms of the empirical rule. And the empirical rule applies to the probability of certain situations occurring. So from earlier in the course, you learned about what it means for data to be normal or approximately normal. So I want you to consider for a moment the bell curve. Now, when data is approximately normal, that means that the mean, median, and mode are all in the center. In reference to the mean, if we go one standard deviation value to the left or to the right, that means mu plus one standard deviation and mu minus one standard deviation. That will contain approximately 68% of our data. So to the left one standard deviation, to the right one standard deviation. Please excuse the graph distortion here, but that contains approximately 68% of your data. If you take it a step further and go 2 standard deviations to the left and right, so mu plus 2 standard deviations and mu minus 2 standard deviations, that's going to contain now 95% of our data. So if you go between, that is 95%. And third, if you look 3 standard deviations away, that's going to contain approximately 99.7% of all of our data. So why is this useful information? Well, this is useful for quite a few reasons. Now, first and foremost, it tells you the composition of your data, or it gives you an estimate. But think about this for a moment, like with our test scores. So let's go back to this example. We had a mean test score of 87.2 with a standard deviation of 8.1. So consider from before, mean was 87.2, standard deviation was 8.1. So if we look at that on the normal curve, the mean is in the center, so that means most people scored 87.2. So if I want to fill in, let's say, one standard deviation to the left, that's going to be 79.1. And if we subtract off another standard deviation, that brings us to 71. So that means 2 standard deviations on the left is a score of 71. Subtract one more, 62.9. On the other side, we can also fill in that information. 87.2 plus 8.1, 95.3. 103.4, and 111.5. Now, think about that for a second. We talked about common sense a lot today. So, in terms of this type of problem, we're saying that 68% of the class scored between a 79.1 and a 95.3 on the test. 95% of the class scored between a 91 and a 103.4, and then 99.7% between a 62.9 and a 111.5. So why is that important? Well, you'll notice the further away you get, the fewer and fewer people that are going to land in those categories. And that's something once we get into chapters 4, 5, and 6, you're going to learn a lot more about. Now, in terms of what we're learning with this section, you have to consider anything that is over or under 2 standard deviations away is going to be considered unlikely. So if I said to you, I took the test and I scored a 105%, land me somewhere over here, that would be considered unlikely. Similarly, if I scored a 40% on my test, that's way out here somewhere, that would also be considered unlikely. Now, let's get back to the concept of why standard deviation is so important, and looking at our data in context is so important. And that's using the coefficient of variation. So earlier I said, hey look, there is a way to tell you how much variety there actually did. And regardless of if it's population or sample data, it's always the proportion between the standard deviation and the mean of your data set. And you'll notice here, even though there's 2 formulas, those symbols are completely insignificant. It is entirely about standard deviation divided by the mean, always, and then multiply it by 100% to convert it to percentage. So let's take for a moment, I'm going to give you the scores from 2 different classes. Let's say I have multiple sections of Math 255, and I want to know, are they scoring consistently, or is maybe there something strange going on with their tests or whatnot? So let's say that Class A scores a 91% with a mean of 91 with a standard deviation of 20 points. And Class B has a mean of 81 with a standard deviation of 5. So generally we say that if the standard deviation is lower, that's a good thing. But one thing we also have to consider is whether the standard deviation is lower or not. What does the mean look like? How much variety is actually in that data set? Because if you have a mean of 91, that means your class on average scored better. However, there's much more of a split as far as the scores go. So take for a moment our coefficient of variation for Class A. That's going to be 91 divided by 20 times 100%, which gives us approximately 22% variety. The coefficient of variation for class B is going to equal our standard deviation. Oops, wrote this backwards, sorry. 20 over 91 times 100%, much better. Our coefficient of variation for class B is 5 over 81 times 100%, giving us a variety of about 6.2%. So here's the interpretation part. What does coefficient of variation mean? The lower the percentage, the higher the consistency is in your data. So we actually want a lower percent. So the lower the percent means high consistency. Now, on the other hand, if you have a high percent, that means you have low consistency. So if I were to ask you something like, which class scored, better, that's open to interpretation, but use the coefficient of variation to determine what that might imply. It looks at first glance a mean of 91 that class A did better, but 22% variation means that your scores were all over the place. You might have someone who got a 40, someone who had, 100 with perfect whatevers. But on the other hand, with class B, you're looking at a coefficient of variation of only about 6%. So even though it looks like they may not have scored as well, that means that as a class, they were much more consistent in their scoring than with Class A. It's more likely that Class A had students failing than Class B because of the higher variation. So that's not the only thing we learn, but it is one of the things that we learn. Now, this concludes our section on measures of variation. In our next video, we will explore measures of relative standing.